For the beginners, I can say x is a set equipped with an order and x y belong to this, then this statement, this is what how they are related. Obviously, you can have this very feeling. There are two elements x y in a set x, they need not be related. They may be related, they may not be related. So, what is, if you look at here x cross x, R is a part of x cross x, R can be equal to x square, that is x cross x, and in that very situation you will get the natural results. What the result you have? If you take your relation to be universal, they will be what? They will getting with the natural form of the result. This is the reason. So, I skip these things, order and other definitions, something over there I would like. So, here two elements are related about order, preceding, succeeding, all these business I hope that you know. Now, here you have another definition the same way. What is there? Ordered set, then an element. This is what is called as upper bound or lower bound, and then supremum and infimum. This all you know, because this we have already done in the real analysis. There I am also realizing that need not to be explained. Like if there is a set, there is an order, all those kinds of notions which you use in early mathematics. Upper bound, lower bound, greatest lower bound, least upper bound, all these facts are there. These are illustrated in these definitions. Now, next is what here unordered is called, this is the complete lattice here, definition 1.4. This is also there, sometimes we are using that an ordered set is said to be a complete lattice if every subset of x has infimum and supremum. This is the definition our student used to study at lower level in our MSc classes. Now, and here now the first thing is look at the order preserving. You have x and y are related, and how about t x t y? This is something which should be noted. Like here, if you take x and y are related, how about the image t x t y? They may not be related. So, this definition restricts that x and y is related. This definition says that their images are also related, and this is essential because this is the fact we will be utilizing in the construction of the definition, how you have the sequence of the traits. Now, next thing next definition is this is what about the metric spaces here, because since we are going to work with the metric space x d, on this you have an order, and then you have the completeness or other definition. So, here one thing I would like to say point out, because you all know that they are with respect to metric completion or continuity or something, all these results that we have tried to improve later. So, this is a complete, this triplet, what I am saying over here now, instead of considering a pair, now you have a triplet x d and equal to or less, means you have a triplet whenever you call a metric space. So, this is also, now here comes that result I was quoting. This is a very famous paper, and this is often referred by the working by our youngsters utilized. I think it has very frequently cited, and here is the theorem's statement. First is what, that x and t x they are related. Okay. Like you take a point x naught and then corresponding image t x, generally what happens, they may not be related. Here first restriction we require is what, that they are related. This is the first restriction we have, and then this is the relational contraction, is just they call it relational contraction when x y are related. To look at this definition of the contraction is not the contraction we work. This is with respect to that order, and x d is complete, t is continuous. Here continuity of t is taken. The reason is what, that here theorems often have two facets. First is what you prove, that there is a fixed point. Thereafter, you prove whether the fixed point are unique or not. That is the reason why you have that t is continuous. Like in the case of the contraction map, t is always contraction, but not only contraction, this continuous, but it is uniformly continuous. But look at here. In our case, we cannot say. Therefore, we have taken that this is continuous. The map is continuous. This is the condition which has been imposed, and x d is complete. These two conditions are in the natural setting. Recently, we have adopted in our ordered theoretic setting that these two can be also like R completeness R continuity, they will come thereafter some time. And here is the sixth condition. This ensure you how you will get the uniqueness of the fixed point without this here. So, this condition is there to ensure the uniqueness of the fixed point. Now, as you see, still it looks very natural, conditions look very natural, though you can say nothing can be more natural like Banach contraction principle, but this is also natural in our context. Now, two fellows, Juan Nito and Rodrigo Lopez, Juan Nito and Rodrigo Lopez, they have utilized this result slightly some kind of modification. One case is what the map is increasing, other case is map is decreasing, and that formulation is look at here. Though T is increasing, just look at there, that was the case, both cases were open, like either they are increasing or decreasing. They choose in the first theorem, this has come to in 205. Look at that very result came in 204, this very result came in 205, where they choose to T to be an increasing map, and then you have this sequence having convergence, and here it has been added. If it is there convergence in K, then increasing sequence such that x n converges to this, then x n and x they are related. That is what is how it is taken. And again you have the same condition you have in that very case, and here you have another contraction that you call again relateless contraction, because whenever x and y are related, once he has taken the increasing, it should be taken as if x equal to or less than this. Then T has a fixed point. This was in fact Juan Nito and Rito Lopez have two papers. One paper in order, general order, another paper is Academica Sinica, that is published English version. And now another result of the similar kind here you have, that is theorem 1.3. What is there? That only two conditions they have replaced by these two conditions here. First thing, second was replaced by second dash, that is T is continuous or x d satisfies the following property. Here if they can, x n is a decreasing sequence, because he has to do decreasing sequence here. X n is a sequence in x such that x n decreases to x, and x n equal to or greater than x. This is what is meant by there. This means they are continuing decreasing sequence. Then there exists x naught such that x naught is T x naught. So, these are the two things, because here we often have equal to or less than. So, in the case of the decreasing map, they took that x naught is equal to or greater than T x naught. And then the conclusion of the previous theorem, that is another theorem we used to hold, and here in the following lines you can see under what conditions you can have the unique fixed point. With that very condition along you have over there pairs, and then global convergence of the successive approximation. Where is that? Every pair of element x has a lower bound or an upper bound. Okay. So, it was slightly light under the condition they take every pair of elements of x has a lower bound or upper bound. So, this was at another theorem Nito and Lopez, and here the third theorem. This came again into now here is another theorem which came in 207, and the theorem is as follows. Here you just look at this, that complete order metric space x d tau T is monotone, means it includes both the cases, unifies, and T is a continuous map, this such that it satisfies the following properties. There is a sequence x n converges to x, where consecutive terms are comparable. Then there exists a subsequence, obviously x n k, such that this is comparable to x, and comparable here sometimes we have used the utilize big bracket x n x, and that amounts to say either x n equal to or less than x, or x n is equal to or greater than x. So, he was and then again you have the last part, and you have that. So, just look at the difference is very little, like sometime he used to take increasing condition, decreasing condition, and very slight improvements are there. Now, and in all the cases we have not said the order we have considered is partial order. It is not mentioned over here, but in all papers right now from beginning our order is partial order. Partial order means reflexive, antisymmetric and transitive. So, the relation which enjoys these three properties in all these papers, this is there. Now, when our journey over here is very accidental, we were working sometime here and there, and we are not daring as if such thing is possible. In fact, here there is a very recent paper at that very time, that was Hashim bin al-Mashayikh. Hashim bin al-Mashayikh removed rest of the two conditions, that is reflexivity and antisymmetry, just using the transitive property. He was able to extend this theorem, these two theorems. Like here the partial order, the improvement was this, that the relation they consider is, our ordering is partial ordering. Here that is not mentioned because in the paper it is not mentioned. That is why the typist has not included that this is a partial. In fact, this is partial ordering. Now, Hashim bin al-Mashayikh, what he did? He has relaxed two conditions, that is reflexivity and antisymmetry in the partial ordering, and then he was able to prove this very result in the same way, and his paper appears, I think, 16. Now, here what we are trying to do over here, we started working whether this very result is possible for a arbitrary relation or not. So, I was just in the company, Dr. Aftab, which is very much over here, was trying this thing, that whether this result can be proved for an arbitrary order or not. Means, like this very ordering which you consider, yes, this is the result. Yes. So, here we are able to relax this very condition like ordered property up to the extent of arbitrary relation, that amorph or bi relation, and later we realize that this condition is very tight. While proving also we are finding difficulties, but after it was through and we were happy that the proof is okay, because I talked to Aftab that you have to be very careful about the proof. I was also very fine because the condition is very tight. It is not be, maybe we are having somewhere committing a mistake, but that is not the case. But finally, the proof was okay, and then after that we submitted this paper to a journal, initially to the proceedings, but it was not forwarded as the case may be, and then we have submitted our paper to fixed Journal of Fixed Point Theory and Application. So, this is so this is the theorem we were established this. Here our operation, our relation R is a binary relation. It does not have all three properties. The improvement accomplished is very little. That is what, that conditions of reflexivity, antisymmetry and transitivity all got relaxed, and here we have in the same condition, that just look at this R complete and R complete. Okay, one more thing. After this we attempted to relax the condition. There is another paper we have written, that refinements through the relational contraction principle, where we have included this relational version for these conditions like R complete and R continuity, and it is suitably defined because all previous theorem they were all natural, like x d or relation R or whatever is said, that is natural setting. Natural setting means they all refer to x d with the topology of D, that what is discussed. Now, here in that very paper we are able to relax and have that very formulation. So, R complete means completeness, means a relation R which are related, means terms are related, as you have maybe ordered sequence, their limits are there and their Cauchy sequence converges, that is the definition. And same thing used in the continuity, that T x n converges to x, this implies T x n converges to x. The sequence is what? those relational sequences means either increasing or decreasing, that the case may be, and x n x either x is equal to or less than x n is equal to or less than x, or x n equal to or greater than x, that could be the case, both cases. And here you have another thing, that in the for the fixed point you are working here, the problem that T x is R s connected, that previously you do not have such definition. Just look at this here, T x is R s connected now for the uniqueness part, and T is R here R preserving contraction, and here T our sequence is R preserving sequence, whatever is the order that is preserved. So, we are referring to the constraints of preservance, that is the case. अब इसका प्रूफ आप जो है वो चंद लाइनें देख सकते हैं, कोई बहुत मुश्किल नहीं है. Look at here, by the first condition we are able to have the sequence of iterates, you are master, x naught is related to T x naught, and by T closeness we have defined as the T closed, like x y belonging to x, this is a heavy condition, then T x T y belonging to R. So, x y belonging to R, this is the condition we have utilized, this is a tough condition, as you can say in the Banach contraction principle, everything is very natural, but the conditions of contractivity and completeness is very strong, very stringent, but the fruit is wonderful, but the condition are very strong here too, that T is closed means x y belonging to R, we refer that T x T y belonging to R, that is the condition we have used. So, x T naught x is equal to or less than T x, now using that is what x T x naught belonging to R, and then by using the T closeness you can have this sequence constructed, that is here, this sequence, and now this is going to belong to R by the T closeness of this, and thus what you have in our notational case, that x n plus 1 belong to the relation R. Now, up to here everything is okay, just by recursively operating our definition you have come over here like this, and by our definition, that is what called relational contraction, this is equal to or less than that, and operately n times as you do in every case. Here is you have the using the triangular inequality, and then this, and then up to this, and this is replaced by a infinite series, this by infinite series, and then this is equal to or less than this, which tends to 0 as m tends to infinity, and this gives you that this course sequence is Cauchy, and then you have the limit up to here, and by continuity you have the fixed point. By using the continuity here, continuous R, then x n plus 1, this converges to T x, at the same time its limit could be x, and by uniqueness of the limit this could be T x, that is the case. So, you have T x is s, this is the same thing as we have in all standard books in MST, that is what you can call that x is a fixed point of T. Now, what you see over here, if R is D self closed, here you have taken the definition D self closed, look at this, x n is R.
So, x is the limit of x n, okay. R they belong to R, x n belong to R.
Yeah.
Limit and x n, R comparable means belong to R or not.
What is the problem?
How is like this? So, x n goes to x.
Yes.
Is it?
Yeah, this both cases, two cases, either this or this. This they have denoted in the paper.
Not.
Yeah. No, this is if you take increasing. Yeah.
Continuity is not needed.
Yeah. Which condition?
That R continuity is not needed. Which is R contraction, not needed.
But that is I got your point. You are right. That is the consequence. As you know, here he missed the point that every contraction map is a continuous map. Similarly, every R contraction map is a R contraction. Right, agreed with you. This here, thank you. You are correct. Now, what you see there is sequence x n k, x belongs to R for all k belonging to n naught. On using assumption, you have this very thing here starting. Here x n k, you put the value here, this is there, everything is okay. Here x n plus 1 turns to here. Now, that was the case here. The other part is what, that is the uniqueness of the fixed point. This is slightly new, as you have made the effort. That we have taken is what, that our path, it is path connected not in that sense we have in topological spaces, that in topological spaces we define path is a map from a closed interval to the topological space. That is not the case here. Here path means a discrete path. Between 2 points you have a finite sequence which you can join them, these 2 points, like taking one initial, another final, and you join this just by x, y. Now you have a sequence, suppose this is z naught and this is z k, this you take as b or x, but I take a b because then you have a sequence here that is equal to or less than z 1, equal to or less than z 2, equal to or less than z k, such that z 1 here these sequences z I, z k I running from anywhere, these are we call as order preserving sequences. So, the order is preserved, that is the case. So, here we have utilized that very definition as if the to prove the uniqueness, here you start from here, and T x inductively you have T n x is equal to x, T n y is equal to y, and these 2 points belong to x, and therefore, here we are using R x connectedness. There exists a point z 1 z 2, a sequence, finite sequence z 1 z 2 z k, such that this is the initial point and that is the final point, and here these sequences are order preserving, that is z I plus 1 belongs to R for each I. Now, as R is T closed, by using proposition 2 we have this belongs to this, and for each n belonging to n naught, you have here d x y, and you have put this thing d to the power T n x z naught T n z k, and now you utilize those points that z 0 to z k just by putting over here this inequality here. We are using triangular inequality, and you got from here up to here this thing, because we are inserting the points here like T to the power n z naught, and then z 1, then z 2, and then finally z k, and from here you have this thing, and you apply time and again our contraction conditions, alpha times this, again alpha times this here, and then alpha times this, and this you have this thing. So, here I is equal to 0 to k minus 1, this thing which tends to 0 as n tends to infinity, okay, and getting us that the fixed point is unique. This condition was slightly different as the case may be. Now, what happens here are the consequences which you have, that in our case under the universal relation R is equal to x square theorem 2.2 reduces to the classical Banach contraction principle, because if you look at the conditions they all got subsumes, and you have the classical Banach contraction principle. Setting R the partial order theorem 2.2, we obtain theorem 2.1, 2.2, 2.3 of Nito and Roderick Lopez. Assumption B, T close is equivalent to increasing property of T. That is what is said here. So, this is T property, this is just an observation, and next theorem is what? The setting R is equal to or less than this, the dual relation associated with the partial order, this in theorem 2.1, we obtain theorem 2.4 and 2.5 of Nito Roderick Lopez. Clearly, assumption B, what that T is closed is equivalent to the increasing property. That is trivially there. You have this is increasing property. Okay, theorem 1 of like the observation 4, particularizing R by pre-order in theorem 2.1, we obtain the theorem 1 of Tunisi. Here transitive relation we get, as I mentioned earlier in the beginning, that the motivation for our work was this paper of Hashim bin al Mashayikh, that was 2.2 and 2.4, and we were able to attempt this so as to improve our taking care of transitive property of this. And here you have finally a indirect kind of thing, that certain paper of Tunisi and Samit, these two are most active fellows, Tunisi, I feel sorry for Tunisi because Tunisi has done good results, but he is not able to present them properly, because initially we just look at the idea, all idea that can be largely attributed because we are doing somehow following refinements here and there, but main content whatever was initiated, that was Tunisi. But one drawback is over here, that he is not wonderful in presenting, he is not able to write his paper properly. Otherwise, his whole idea was exploited by what Ryan and Runing, and write that very beautiful paper, which is often read by everybody in the proceedings. Now here, okay. Now here is, there are 3 examples here, and I may recall my role as supervisor to Dr. Aftab Alam. When the theorem was proved and we were somewhat convinced that the theorem is proved, then I asked Aftab, prove that how it is different to the other theorems. Aftab was complaining to me that submit the paper. I am saying no, I will not submit unless you come out with the examples. So he worked hard for quite some time. Then he came out with 3 examples separately, so as to justify that this very result is a genuine refinement over the result of Hashim bin al-Mashayikh. And after that I submitted this paper, and when I got the revision, there was nothing in it here and there, and the referee was satisfied, fortunately for our point of view. And here is the first example. Here R is our natural setting, my binary relation is this, means x is equal to or greater than y, and this is obviously partitions the R to x cross x into 2 sets equal to or greater than less than this one part he chooses. And then you have our map here, that is T x 4 plus 1 by 3 x. Clearly R is T closed and T is R continuous. And here you have the contraction condition, everything is okay. Now what we need to show is what fixed point. T has a unique fixed point. Here you have the RS connectedness of this. You can very easily feel that this space T x is what? T x equal to or greater than y, this T x is always there, and here we have no problem because it is whole half plane. You can always have the finite sequences, this is there, and therefore unique fixed point because of closeness. Now another example, here we have, this is all done by Aftab, full marks to him, because I only said no, I will not submit the paper unless you have examples. I only credited, I said no, you cannot submit the paper. Here this, the map we have considered, here is the domain you have taken 0 1, just uses 5 elements. For the youngsters, for our seniors, they are very sharp, as Professor Dhage has pointed out a very interesting observation. Very interesting observation, thank you. So just look at here. 5 as many as 5 elements for youngsters. If you know, if your contraction survives on these 5 points, 5 x, you are fine. Any contraction map that need to survive only as many as 5 points here in the relation they are active. Otherwise, in the other spaces, in the other part of real line, no problem happens, you don't care. Then you have here, just to look at, because of T x 0 and 2, they are not the part of 2 x. Here they are the part of outside, and therefore only thing you have is what, then 0 and 1, they are the part of this, that our ordered sequence or order preserving sequence, that is only this one, 0 1 0 1 and 1 1 for all n belonging to n, which gives rise xn as a sequence which is the part of this, either these 2 elements. And 0 1 is closed, as you know, we have all these conditions are satisfied, and you may have that the contraction condition that you can very easily verify, and thus all the conditions you see in the theorem are satisfied. But look at what is the advantage here. Notice an example 2, the binary relation R is not any one of the earlier known standard binary relations. So this relation, such as reflexivity, irreflexivity, symmetry, anti-symmetry, transitivity, completeness, as well as weak completeness. So this again shows one aspect of the game, that this is a genuine improvement over the other results which have already discussed many. And now finally this result. The open interval 0 1, you have taken as your setting. This is not complete in the natural sense, as you know. Here you can find that this is R complete. So, this 0 1 is not complete, but it is R complete what is there, and oh, that is example 3. Just look at here. Example 3, the ambient metric space is incomplete, which is R complete. Just look at this first observation, that 0 1 naturally you have excluded the point 0, that is why completeness gone, but it is R complete, and underlying map is not continuous, which is R continuous. So, and underlying map is also not continuous as far as the is not continuous, which demonstrate the only existent part of theorem 2.2, but not uniqueness part. I am talking about completeness of T x, because you have seen that we are talking about T x whenever talk of the uniqueness. So, T x and T x is what 0 1, okay, that is there. So, these three theorems situationally, what is this? These three theorems situationally prove that there is an improvement. Now, I will not tell you this is very significant, very somewhat refinement. This is a refinement over all previously known results, and this came to when he started trying to extend this theorem to Boyd and Wang type contraction condition. They do not survive like this condition, Boyd and Wang type condition, everybody knows d of T x T y, this is equal to or less than phi of d x y. We have already literature on this, and we have also worked on this. So, here the arbitrary relation does not survive. We need an additional condition, arbitrary condition. It does not survive. Why? Because of the requirement, because we need to have our another function which we define as locally transitive, local transitivity, and thereafter we are able to prove this result. So, what I am trying to say that the improvement is little but not very significant, because we are not able to get one example so as to say genuinely this is different. That is the case. This is what I personally feel. Now, this is what we do, and there are two papers for this. You have to look two papers. One paper is Journal of Fixed Point Theory, another is in Axioms. I think Axioms, Filament, refinement to refinement. Another, yes, no refinement, that is there. So, there are three papers in all. You can just look at this. This is the initial and very natural, very simple setting. I think anybody can do it as far as my observations are concerned. Now, we come to another part of this. How much time I have? Chaliye, let us go. Now, here we have first observation for the youngsters. I am not saying anything for my seniors. Maybe here, as soon as you take the non-expansive map, what happened to the literature? Like if you take a non-expansive map, here I will be talking, there is nothing other than Professor Muhammad Amin Khamsi. You will see here its contribution. I will just state the theorem, because maybe you feel very taxed if I go through the proof. What is very wonderful about this is what you take any sequence of iterates x n in x d, x n converges to x, okay, which is fixed point. So, any sequence of iterates, as I have said in the beginning, the conditions are very terrific, contraction and completeness, but the result is wonderful. You take a point of iterates these days, you construct a sequence, limit point with a fixed point. So easy. Even if you do not know, you can very easily do it using the computers. But what will happen to this very thing, to this case? as far as non-expansive map is concerned. Non-expansive means distance cannot increase, maybe it can be equal. What happens? This result is no more there. Then x need not converge to the fixed point of t. What I have taken t is to the fixed point of t. That is a very simple example you can utilize and you can convince yourself. Just you take x is equal to, because I am taking on the metric space, x is equal to minus 1 to 1. This is you can find in many books, and you take here T x is equal to, define the map T x is equal to minus x. The sequence of iterations need not converge to the fixed point. Yes, have some idea? Any point you take which is non-zero, it need not converge to the fixed point. Just look at this fixed point is what? Is 0. Just look at this map, T x is equal to minus x. So, T x is equal to minus x, and fixed point is obviously 0. Here you look at the fixed point is 0, but iterate at a non-zero point, iterates for a non-zero point, does not converge to fixed point of t in general. That is what I am trying to say over here. Now, then obviously plane may not be the case, and those who are having interest here, many like Professor Khamsi's area. This is the Professor Khamsi's area where he has done a lot, contributed very significantly. Then how about the results, possibilities to prove the fixed point result? So, in this regard there were 3 papers simultaneously, one by Broder, another by Johad, and another one above all most general, that is by William R. Kirk. So, William R. Kirk has proved a theorem, and these 3 papers came simultaneously in 1965. So, this came simultaneously in 1965, and they are still often referred here. Now, I am having first result before you on the Hilbert space, a self map or a map mapping to a closed bounded convex subset of f h. Then here your this is the existence theorem, then there is a fixed point x. You cannot have the construction procedure before you have the iterative processes as you have the case. So, in this regard there is a iteration scheme process, a lot of literature is there, many iteration schemes are there, but here only existent part, that there is a fixed point x such that T x is equal to x. So, just out of these 3 condition is very simple. As you know, your Hilbert space fitting is wonderful. This is very natural, geometrically as well as in many ways to prove the theorem. So, this is the most natural result. This came in 1965, and then another result. Oh, क्या हुआ? इसको कोई गड़बड़ हो गई सेटिंग. Yes, yes. ओहो, उल्टा यार. Yes, next. Then here first the definition is required so as to state the next result, that is uniformly convex Banach space. So, this property is well known, we used to teach at the MSc level, like we know the geometric property. What geometrically says that any 2 points joining on the ball, you take geometrically, unit ball, or the case may be, the midpoint may not be on the ball, but they should be very close to the ball. That is the definition we abstract, and here you have the definition is equal to or less than, and the points are very close, is still their midpoint does not lie on the space on the ball. And our student, MSc student, they may recall their book, the case may be on x equal to R2, Siemens book, and they can very easily infer about these balls. I do not want to mention the ball here. This picture you may have in your mind. Siemens book, especially topology, this is there, and there is one more on this very figure. This is the Siemens book. Look at with the natural ball on the R2 itself, not Rn. If you can have this generalized, the natural ball with Rn with R2, they are always uniformly convex, because if you take any 2 point, the midpoint, this will be not the case with this or with this, but here if you just look at any 2 point, they are very however close they are, the midpoint definitely this will not be on the circle or on the circumference, but this will be very close to this. So, here the other examples which is indicated over here. Here with this definition like that is mentioned in this here on the Rn I have mentioned, but if you r is equal to 2, you can very well see this diagram, and these are what the balls centered at 0 0. As just look at this, like if I remember some of x plus y equal to or less than, some of the properties are what will be here, mod of x plus mod of y for equal to or less than 1. One of them is this. Here of course, x y they are in the ball, and this is the natural ball, and then maximum, minimum, so many things that is there. So, here some of them, what this example says that this is not a property which is of the set, this is a norm property. Same set with a different norm may be otherwise. So, R2 with some other norms may be not uniformly convex. So, here this very theorem is what uniformly convex Banach space K, a bounded closed subset and convex subset X, then T from K to K non expansive mapping T has a fixed point. And then came here definition of non-diametral points, or you can say we are looking towards our Banach spaces here a normal structure. So, two terms are involved, that is reflexivity and normal structure. So, this theorem cannot be stated, though this is the most general result what is here. So, here you have the non-diametral points, the first definition 2.3. Here is the definition that when a space Banach space is said to have the normal structure. So, it says what, that every closed convex subset of a Banach space with diameter equal to this has normal structure. And here you have diameter as the case supremum. So, we may start our students teaching what is the diameter. By the way, what is the diameter of a circle if you use this method? Suppose I have a circle of radius r, what will be the diameter? बोलिए, कुछ तो बोलिए. Is it the same definition or otherwise? Or the natural norm? It's natural. What do you look at? Diameter of a circle? Yeah, there can be more distance than this. समझ नहीं पा रहे. I am asking you whether this natural definition coincides, this abstract definition with the natural definition? Yes, definitely yes. So, here and reflexivity, as you know, that natural embedding that is onto x to x double star. Okay. This map, this is onto, or there are other ways here. There is also one more definition. So, now normal structure, here is the fixed point, the theorem 3.2 due to William R. Kirk, a great man who has written many books. The books by Gobil and Kirk you must not have forgotten. The book by Samin Khamsi and Kirk, that too is very handy these days, and many other ways he has significant contribution. Professor Kirk, here is another paper by him, and that is very significant, and this is the most general. What is there? X is a reflexive Banach space equipped with a normal structure, means whose every closed bounded convex subsets of X are having the normal structure. Then K has a normal structure, have sets. Suppose that K has a normal structure, then T from K to K is a non-expansive map, then T has a fixed point. These are 3 related papers, all came in 1965, and many things I have to say, but I do not have time here. Like Hilbert space has never fixed point property. You define the right shift operator, it does not have the fixed point property, and many more. A lot of literature is there, but I do not want to go here. I want to come to the, as I have said, that without Professor Naveen Khamsi nothing is possible. Here is the first result. Yes, here he has considered a partial Banach spaces. Okay, partial means a Banach space which is equal to the partial ordering, and we say that T from X to X is monotone, and this is what we call monotone non-expansive mapping. I have not mentioned over there. Then with X equal to R this, then T is called a monotone non-expansive map. So we define a monotone non-expansive map means the partial ordering is there, in that we consider monotone means increasing sequence of elements, and then you have this monotone mapping. Okay.
And normal compatible. Is there any compatibility between norma and order?
Yeah, sure, definitely. That is true. That too is there. But here we have taken the ordered monotone. We have named the word monotone. Okay, so that is obviously cases, both the cases we have. And then Bacher and Khamsi, there is another definition. Now here you can have this increasing interval or interval in a partially ordered norm spaces. Okay, here is the order. You take an initial point P, and any element this, if such that P x belong to this or P is equal to x, then that is was the case. These two are the intervals, order intervals in the partial ordered set X this, with initial point P and maybe terminal point, or you can say the end point Q. So these are the two. They are intervals. Because of the ordering, these intervals are possible in the even. Now here comes the theorem. Here again Professor Khamsi is available, as I have said in the beginning. When the Haish and Khamsi proved this very result, here is the result, that the partial ordered Banach spaces are there such that order intervals are convex and closed. Assume that X is uniformly convex, K be a bounded closed convex subset of X, and let T from K to K be a monotone non-expansive mapping. Then there exists this such that these two elements are comparable. So again he put this condition, very extra condition, that X naught and T x naught are related, as we have in our theorems. Without construction will not be possible. Then T has a fixed point. So this is the result by Professor Khamsi. Now what we can apply our case situation or relational consideration? What are the improvements which are possible? In these results we adopt, rather than partial ordering, we adopt the relation, our amorphous binary relation. Then these are the improvements we are able to assess here. We worked with some in teams certain points here. Partial ordering can be replaced by a transitive binary relation. Here again I have said that the condition of amorphous binary relation is very tight, but here look at this, up to transitivity we are okay. So partial ordering can be replaced by transitive binary relation. Transitivity of the relation is not needed in the whole space, but it can be limited on a suitable subset of K. With transitive binary relation, transitivity of the relation is not required on the whole space X, but it can be limited to a suitable set. Closeness and convexity of R interval are also not required, but it suffices that merely certain relational intervals in K are closed and convex. Furthermore, convexity and closeness of the whole space are again not needed, but this can be limited. Bounded the whole set K is replaced by relatively weaker assumption, as you see just now. What is the possible result? Here the map, this is ulta chalega kya? No, it is third. I'm not going to the details. These are this is required. Here this definition 3.7. Image of AX, AR. Here you take those elements in K such that AX belong to R or X is equal to A. This is the definition. It is also in X, and similarly here pre-image of AR, that is the reverse order, that you can call inverse kind of situation, that is X belong to R, X A belonging to R and X equal to A. So, if you take the partial ordering on this, if you are these definitions of the real line, then this coincides our interval, which is called closed, like these intervals in the real lines. If you take R and you have this ordering, natural ordering, then these two intervals they reduces to this, as on the case of in the real line. And here is another lemma which will come to our statement. A Banach space X is reflexive, as I have said in the beginning. Every decreasing sequence K n of non-empty bounded closed and convex subsets of X have non-empty intersection. This is one of the lemmas due to Sumilian here 32, and this is not empty. This we utilize if we used to have the statement. Now, here there is a function that you can call this 3.3, this is 3.8, this is also by these authors. As you see, you define a bounded sequence x n in K, X norm space, Banach space, order partially ordered Banach space, or here in our case ordered, and then a function K from 0 to infinity. Here no need is required, nothing is needed. Here tau x is equal to limit superior n tends to infinity x n minus x such that x belonging to K. So, this is what is named is what type function. So, this was named as a type function for a bounded sequence x n in a Banach space. Now, here another lemma, that is again by the same group, that is K be a non-empty closed and convex subset of a uniformly convex Banach space, and K is a map from this to this. Then type function, then T has a minimum, then T has a unique minimum point Z belonging to K such that this is the definition here tau x, tau K. So, there is a unique Z such that tau Z is equal to this infimum, that is there. Now, here we have our results to the extent just look at here, there are three conditions. X be a uniformly convex Banach space and K a non-tree subset of X. Let R be a transitive binary relation on X, then T from K to A and R norm expansive if there exists K such that these three conditions are there. X naught T x naught belonging to R. This is again for the sake of the construction of the sequence. This set image T x and R is a non-empty closed and convex subset of convex for each n belonging to n naught, and T n x is bounded. Then these under these three conditions, that very theorem, as I have said in the beginning, that can be lightened or it can be improved up to this extent that we can utilize our binary relation here. Then T has a fixed point. Okay. So, shall I go for the proof? No. How much time I can take? Finish. Okay. Then let us see the corollary. Now, here is another statement that if R is replaced by R inverse, we call here, though I go very quickly, RS means R union R inverse. So, here if you have the R and then you have the inverse relation, means x y belonging to R implies x y y x belonging to R. So, here there is another possibility to have an analog or a kind of dual kind of result here, if there is decreasing order here, that image of T and x naught is replaced by R, and that way since x T x naught is equal to R less than x naught, you have that, and here third condition is same, then T has a fixed point. Okay. There are many, I have no time, but I wish to tell you that something more we have done here in this regard, that is asymptotically non-expansive mapping. I am stopping here. This is the result we did. This has come in 1922, I think, or 21. But recently we did a paper that is on asymptotically non-expansive mapping along with Hasanuzzaman, where you have utilized these ideas of Professor Ibn Khamsi to prove a result, to prove some results which are published very recently in 2024 in Romania journal, fixed point theory, Romania, that is very recently published. We extended to the theorem of Gobil and Karp. So, that very theorem means asymptotically non-expansive, means that map is non-expansive for t to the power n, as we have the case. So, if t is we have not t non-expansive, but t to the power n is non-expansive, and that very result we have published, and we have also published some example in that very paper, because referees these days ask that how can say your paper your result is better, then we have to construct some example, then we have constructed an example. So, that was the most recent result we have done. What I can say that if you try by some work, not very hard, because all I have is stolen the ideas of Professor Khamsi. I have not contributed new ideas here, just using his ideas we are able to prove such results which are predictable. This is what I wish to thank you. Maybe I am not very good in presenting like Professor Khamsi or Professor Vinayak S. Chaudhary, but definitely I owe a lot. I wish you all the best, especially youngsters, not our senior, they are better than me. So, I wish you all young guys all the best in your future life. Okay. We can discuss sometime here. If you have something to say about this, I will discuss over here. Okay. Thank you.
Thank you very much, sir, for your nice talk in this direction, from contraction to non-expansive mapping, and then finally monotone asymptotically non-expansive mapping. So, if you have any one or two query questions.
Most result is by